Hello my friends and welcome back to the Today Machine channel. The car shredding process is an integral part of the recycling industry, allowing for the efficient reduction of scrap vehicles and other metal waste into manageable pieces. The key machine involved in this process is the scrap shredder, which is specifically designed to handle materials like steel turnings, shavings, and borings, reducing them into smaller, uniform chips ranging from 20 to 50 millimeters in size. The operation begins with the feeding of scrap metal into the shredder's hopper. This can include entire cars, steel parts, and various other metal debris. The scrap shredder features powerful, hydraulically driven rollers, which are the core components responsible for the shredding action. These rollers are connected to hydromotors that supply the necessary torque and speed, ensuring that even tough, dense materials are efficiently shredded. As the scrap metal enters the shredder, it is gripped by the rollers, which pull it into the machine. The rollers are equipped with teeth or cutting edges that shear the metal, breaking it down into smaller pieces with each pass. The hydraulic motors allow for precise control of the roller's speed and force, ensuring optimal shredding performance across a wide range of material types and thicknesses. The shredded material is then pushed through a sizing grate or screen, which further refines the output to the desired chip size, typically between 20 and 50 millimeters. This uniformity in chip size is crucial for subsequent recycling processes, as it allows for easier handling, sorting, and smelting of the metal. One of the major advantages of using a scrap shredder with hydromotor-driven rollers is the machine's ability to handle a continuous feed of material, making it highly efficient for large-scale operations. Additionally, the hydraulic system provides overload protection, which prevents damage to the machine in case of an unexpected obstruction or exceptionally tough material. Steel is endlessly recyclable, capable of being remade, reimagined, and transformed from old to new. This is why steel remains the most commonly used metal worldwide. At Gerdau, their steel production exemplifies this sustainability, with 98% of their steel made from recycled scrap, including junk cars and refrigerators. The process begins at Gerdau's metal recycling yards, where scrap is collected and processed. The ferrous scrap is then transported to their mills, where it is layered to produce optimal heats or batches of steel tailored for specific products. In the melt shops, cranes load electric arc furnaces with scrap, and an immense electric current passes through electrodes, melting the scrap into liquid steel. The electrode tips can reach nearly 5,500 degrees Fahrenheit, about half the temperature of the sun's surface. The molten steel is then transported to continuous casters, where it flows from ladles into tundishes and then into water-cooled copper molds. As the steel strands exit the molds, they form a semi-solid shell while the interior remains soft and malleable. Next, the steel enters rolling mills, where it is shaped by passing through a series of stands with multiple pairs of rolls. The force required to shape the steel is akin to the impact of a car crash at 80 miles per hour. Each stand helps shape the steel into specific products, each with unique properties, grades, strengths, thicknesses, shapes, and applications. With over 3,500 different grades of steel, 75% of which didn't exist 2 decades ago, Gerdau's products are perfected and then shipped to customers, where they become the backbone of modern infrastructure and technology. This section is about producing train tracks in a high-demand steel mill, the one in Bahrain. The process begins with selecting high-quality steel, which is melted in an electric arc furnace. This steel is then cast into rectangular billets, which are the raw material for the tracks. The billets are heated in a reheating furnace to make them malleable. Once they reach the desired temperature, they are fed into a rolling mill. This is where the SMS Group, equipped with Nord Drive Systems' robust drive technology, comes into play. The rolling mill, consisting of a series of roller tables, progressively shapes the heated billets into long, slender steel rails. These rails must endure the extreme conditions of heavy loads and mechanical shocks, making the precision and resilience of the drive systems crucial. As the steel passes through the rollers, it is elongated and shaped into its final rail form. The Nord industrial gears, designed for high torque and efficiency, play a vital role in maintaining the precision and strength required during this process. After rolling, the rails are cooled and straightened using powerful drive systems, ensuring they meet the stringent specifications required for rail tracks. Finally, the tracks undergo quality checks, including testing for hardness, straightness, and surface finish. Rolling mill rolls are essential components in the metal forming process, used to shape materials like steel, aluminum, and copper. The manufacturing of these rolls involves different methods, depending on the type required. Cast iron rolls. These are made by pouring molten iron into molds, where they cool and solidify. The casting process can produce rolls with complex shapes and varying hardness. After casting, the rolls undergo heat treatment to enhance their strength and durability. They are widely used in hot rolling mills due to their resistance to thermal fatigue. Forged rolls. Forged rolls are made by heating steel billets and then hammering or pressing them into shape under high pressure. This process refines the grain structure of the steel, resulting in rolls with superior toughness and wear resistance. Forged rolls are typically used in cold rolling mills, where precision and strength are crucial. Both types of rolls undergo final machining to achieve the desired surface finish and dimensions, ensuring they meet the stringent requirements of rolling mill operations. The manufacturing process of an overpack for high-level radioactive waste made from carbon steel is a meticulous and highly specialized procedure. An overpack is a crucial component in the safe storage and disposal of radioactive materials, serving as an additional layer of protection against radiation leakage. This section shows the various stages involved in the production of a carbon steel overpack, from forging and machining to welding and final assembly. Forging process. The first step in creating a carbon steel overpack is the forging process, which involves heating the steel to approximately 1000 degrees Celsius in a furnace. At this temperature, the steel becomes malleable, allowing it to be shaped and formed. The raw material, which is cut from larger steel blocks, is initially forged into a cylindrical shape, which will eventually become the body of the overpack. This cylindrical body is then subjected to a 2,000-ton press, which applies immense pressure to adjust the overall thickness of the material. The pressing process also involves fine-tuning the edges of the cylinder to ensure uniformity and precision. This sequence of heating, pressing, and adjusting is repeated multiple times to achieve the desired shape and dimensions. Once the forging is complete, the overpack body is allowed to cool naturally. Edge refinement is crucial as it ensures that the ends of the cylinder are perfectly flat and aligned, facilitating a secure weld when the lid is attached. Once the final shape is achieved, the forged cylinder is allowed to cool naturally. This controlled cooling is essential to avoid internal stresses or warping, ensuring the steel retains its strength and durability. After cooling, the cylinder undergoes inspection to confirm that it meets the required specifications before moving on to the machining stage. Machining process. After the forging process, the overpack body undergoes machining to refine its shape and prepare it for the next stages. The cylindrical body, which weighs approximately 5.1 tons, is mounted onto a lathe for this purpose. The machining process involves both internal and external cutting operations to achieve the precise dimensions and surface finishes required for the overpack. The machining of the overpack lid is also a critical step. The lid, which weighs around 300 kilograms, is machined separately but with the same level of precision as the body. Both the body and lid must fit together perfectly to ensure a secure seal during the final welding process. Welding process. The welding process is arguably the most critical stage in the manufacturing of the overpack, as it ensures the integrity and safety of the final product. The welding process begins with preparing the body and lid for welding, which includes aligning them correctly and ensuring that all surfaces are clean and free of contaminants. The body and lid are welded together using TIG, tungsten inert gas, welding, a process known for its precision and strong welds. The welding begins at a depth of 19 centimeters from the surface and proceeds at a speed of 6 to 10 centimeters per minute, ensuring a controlled and consistent weld. The welding process is conducted in multiple layers, starting with the deeper layers and gradually moving towards the surface. The final welding layer is completed at a depth of 2 centimeters from the surface, ensuring that the entire weld is robust and secure. Final product. Once the welding process is complete, the overpack undergoes a series of inspections to verify its quality and integrity. These inspections include non-destructive testing methods to ensure that there are no flaws or weaknesses in the welds or the material itself. Loading of threaded grinding wheel. The process begins with the loading of the threaded grinding wheel. This is followed by a patented dressing concept that eliminates the need for setup, ensuring the grinding wheel is ready for use quickly and efficiently. The dressing of the threaded grinding wheel involves two critical steps: dressing the left flank and right flank of the wheel. The dressing unit swivels automatically to achieve this, ensuring precise and uniform dressing on both flanks. Additionally, the machine automatically adjusts the coolant nozzles to optimize cooling during the TWG process, which is crucial for maintaining the integrity of the gear surface and the grinding wheel. Roughing with threaded wheel grinding. In the roughing phase, the Titan 1500G utilizes the threaded wheel grinding process for maximum productivity. The use of a rough grit size allows for efficient material removal. For example, when grinding a gear with a module of 14/84 teeth, a face width of 255 millimeters, and a helix angle of 11 degrees, the machine can achieve a 36% time saving compared to conventional profile grinding methods. This makes the Titan 1500G highly efficient for high-volume gear production. Tool change and profile grinding. The machine is equipped with a fully automatic tool change system that can switch between TWG and PG in less than 1 minute. This system supports up to 4 tool stations and eliminates the risk of interference between the workpiece and grinding tools. Once the profile grinding wheel is loaded, the machine automatically adjusts the coolant nozzles to suit the PG process. The dressing of the profile wheel is then carried out on both the left and right flanks, similar to the TWG process. This is followed by the profile grinding phase, where the wheel grit size is selected based on the required surface finish, ensuring the highest quality output. power grind for larger modules. For larger modules, up to 44, the Titan 1500G is equally effective. The process begins with the dressing of the roughing grinding wheel, followed by roughing with the profile wheel using a rough grit size. The machine automatically adjusts the coolant nozzles for this operation, ensuring optimal cooling. For a gear with a module of 25/18 teeth, a face width of 495 mm, and a helix angle of 19.6 degrees, the machine can achieve a 30% time saving compared to conventional methods, with a surface finish of raw less than 0.2. The fully automatic tool change system is utilized again, followed by the dressing of the finishing grinding wheel. The profile grinding process then ensures the highest quality, with the wheel grit size selected according to the required surface finish. The Titan 1500G is an advanced solution for gear grinding, offering significant time savings, high precision, and flexibility across a wide range of gear sizes and complexities.
Clamping is only manual, yeah? Workpiece clamping, yeah?
I don't know what you mean.
The clamping of the workpiece.
Yes, yes.
Yeah.
Everything is all right with this.
Okay.
Machine has,
The Titan 1500G power grinding machine is a highly advanced system designed for combined threaded wheel grinding, TWG, and profile grinding, PG, of gears. It is capable of handling large modules up to 14 with high precision and efficiency, making it ideal for grinding gears with a large number of teeth. The hot rolling process begins with heating the steel slab in a reheating furnace. The slab, which is continuously cast to the required weight, width, and thickness, must reach around 1200 degrees Celsius to become malleable enough for rolling. The heating process is crucial because it directly affects the material's properties. If the slab is not sufficiently heated, carbides and nitrates may not dissolve properly, leading to undesirable material properties. The reheating furnace typically uses walking beam technology to feed the material through the oven evenly. Surface preparation. Once the slab is heated, it is transported to the roughing mill. However, during transportation, the hot steel reacts with oxygen in the air, forming a mill scale, an oxide layer on the surface. If this oxide layer remains during rolling, it can get embedded into the steel, degrading the surface quality of the final product. To prevent this, the material undergoes a surface cleansing process where high-pressure water, at about 160 bars, is sprayed onto the slab to remove the oxide layer. Roughing mill process. After surface cleansing, the material enters the roughing mill, where it undergoes significant thickness reduction. Originally, the slab has a thickness of about 22 centimeters, but after passing through the roughing mill, it is reduced to approximately 3 centimeters. This reduction is achieved through multiple passes in a powerful 4-high rolling mill, which consists of 2 large backup rolls and 2 smaller working rolls. The backup rolls are typically made of cast steel, while the working rolls, which are in direct contact with the hot material, must have very smooth surfaces and be highly resistant to wear and high temperatures. Throughout the roughing mill process, the material is surface cleansed several times to remove any new traces of mill scale that may form. Vertical rolls are also used to control the width of the material, ensuring it remains within the desired specifications. After this stage, the material is referred to as transfer bars. Coil box and finishing mill. The transfer bars are then rolled up in a coil box. The primary function of the coil box is to save space, but it also serves an essential role in temperature equalization. By coiling the transfer bar, the temperature difference between the ends of the material is minimized, which helps maintain consistency in the final product. When the transfer bar is uncoiled, it has a temperature of about 150 degrees Celsius. The ends of the transfer bar are then cut off, and the bar undergoes further mill scale removal. Next, the material moves to the finishing mill, which consists of 6 stands configured as 4 high rolling mills. In this stage, the transfer bars, now referred to as strips, are reduced further in thickness, down to between 1.8 mm and 16 mm. During this process, an up-looper device measures and controls the line speed and strip tension. The up-looper's swinging motion helps adjust the profile and flatness of the strips, which are critical for ensuring the quality of the final product. Final cooling and coiling. After the finishing mill, the strips are cooled at a rate tailored to produce the desired microstructure and material properties. The cooling process is vital for achieving the appropriate mechanical properties in the steel. Once cooled, the strips are coiled, with the coiling temperature varying between 150 degrees Celsius and 750 degrees Celsius, depending on the specific requirements of the material. This shows manufacturing of pipes, particularly large diameter ones used in the oil and gas industry. Plate handling by EOT cranes with magnetic lifter. The manufacturing process begins with the handling of steel plates, which serve as the raw material for pipe production. Overhead traveling, EOT, cranes equipped with magnetic lifters are used to lift and move the heavy steel plates. These magnetic lifters ensure that the plates are securely held and precisely positioned, minimizing the risk of damage during transportation within the facility. Plate feeding to edge milling by vacuum lifter. Once the plates are lifted and positioned, a vacuum lifter feeds them into the edge milling machine. Edge milling machine. The edge milling machine plays a critical role in preparing the plates for forming. The machine mills the edges of the steel plates to achieve the desired bevel angle and smoothness. The crimping machine applies a uniform bend along the edges of the plate, creating the initial curvature necessary for pipe formation. This crimping ensures that the plate edges meet accurately when the pipe is eventually formed. U-ing press and O-ing press. The next stages involve forming the crimped plate into a cylindrical shape using specialized presses. The U-ing press, developed by Versum Sumitomo, bends the plate into a U shape. This intermediate shape is then further processed in the O-ing press, also by Versum Sumitomo, which closes the U shape into a full circle, forming the basic pipe shape. These presses are critical for ensuring the pipe's dimensional accuracy and structural consistency. Pipe washing one station and pipe drying station, burners. Following the forming stage, the pipe undergoes a cleaning process at a designated washing station. This step removes any contaminants, such as oils, dirt, or scale, that may have accumulated during the previous stages. After washing, the pipe is dried using burners at a drying station. This ensures that the pipe is completely dry before moving on to the welding phase, preventing any moisture from affecting the weld quality. Continuous tack welding and tack repair station. With the pipe now formed and clean, continuous tack welding is carried out. Tack welding temporarily holds the pipe seam in place before full welding is performed. After tack welding, the pipe is inspected for any imperfections at the tack repair station, where necessary corrections are made to ensure a seamless welding process. Pipe numbering and ID/OD welding stations. Once the pipe is securely tacked, it is assigned a unique number for traceability. The welding process then begins in earnest, starting with internal diameter (ID) welding, followed by external diameter (OD) welding. These welds are performed using advanced automated welding stations that ensure precision and consistency. Proper ID and OD welding is crucial for maintaining the pipe's strength and integrity under high-pressure conditions. Tab removal station and OD weld bead removal, pipe end. After the welding process, the tabs used to hold the pipe in place during welding are removed. Additionally, any excess weld material or bead on the pipe's outer surface is removed at a dedicated station. This step ensures a smooth surface finish, which is important for both the pipe's performance and its fit during installation. Pipe weld bead inspection. Pre-Diesel ultrasonic testing machine, UST-1. The welded pipe is then subjected to a series of inspections to ensure the quality and integrity of the welds. Pre-Diesel ultrasonic testing, UST-1, is performed using specialized equipment to detect any internal flaws or discontinuities in the weld. This non-destructive testing method is critical for identifying potential weaknesses before the pipe undergoes further processing. Mechanical expander and final ultrasonic testing, UST2. To ensure the pipe meets the required dimensions and roundness, it is passed through a mechanical expander. This process uniformly expands the pipe, eliminating any minor irregularities in shape. After expansion, the pipe undergoes a final round of ultrasonic testing, UST2, to verify the integrity of the entire structure, particularly the welds. Pipe ends X-ray, ID/OD surface inspection, and end beveling machine. The pipe ends are subjected to X-ray inspection to detect any defects that might not have been caught during ultrasonic testing. Following this, both the internal ID and external OD surfaces of the pipe are inspected for any surface defects. The pipe ends are then beveled using an end beveling machine, preparing them for joining during installation. Dimension check and pipe marking. The final stage of the process involves a comprehensive dimension check to ensure the pipe meets all specified tolerances. Any deviations are corrected before the pipe is marked with relevant information, such as size, material grade, and manufacturing details. This marking ensures full traceability and easy identification during transport and installation.